So good evening, everybody. Thank you for joining us. Sorry for the minor delay there, but we're just getting set up. Thank you again. My name is Daniel Meeker. I'm the president of the Swiss Finance and Technology Association. We're organizing the event tonight, and this is our third online event and networking event of the year. We started off with Women in Innovation, followed by voice bot in banking, and tonight we're going to hear about quantum computing, specifically applied to the area of finance. The Swiss Finance and Technology Association is an independent association representing all stakeholders neutrally, and we work as the center of gravity to foster the development of the Swiss fintech ecosystem. We're a dedicated team of volunteers, and one of our main activities is to organize events like this and to bring together the key stakeholders in the Swiss fintech ecosystem, but also globally through our partnerships and events like this, where we can have people from all over the world attending. As you know, tonight's event is free to attend, of course, but we do have paid events and a lot of in-person events, physical events, of course, which have been very, very limited over the last year, but that would be the norm. And it's possible to join the association as an individual member, a fintech startup, or as a corporate member. And I would strongly recommend joining in this way for the reason that you get a lot of benefits by doing so. And that was maybe just to mention as well, my own, of course, personal journey started with the association that way 2 years ago. And since June last year, I was appointed as president of the association. Some of the things I've experienced and you can expect by becoming a member is to meet a lot of new and interesting people working in some fascinating areas. Tonight is a great example. To join informative and fun events, learn new things, gain insights to the latest topics in the fintech industry. You can have the chance to speak at events, to get involved in committees, share your insights. You could become a mentor. You can find a mentor. There's really a huge amount of possibilities. But what I can say is that so you can pay your membership fee, and that's 100 francs for an individual, just to mention that. But it shouldn't stop there. You have to be, to get all those things out, you need to activate what you're doing. And that's what I did. I started the Basel chapter of the association when I joined. There wasn't one that existed before, and there's a lot of things going on in Basel in Switzerland, and that's how I got into this. And it's just been fascinating and a great journey ever since then. So that would be what I would suggest to you to take your next step after this event, if that sounds interesting to you. So that's my pitch to you. And regarding the event tonight, I'm very excited to hear more about this topic. I don't know very much, so I'm really looking forward to learning more and to hearing the practical applications and the technical aspects that I'm sure we're going to hear. I would like to say thank you to Mario Luoni, who's in our team. He suggested this topic, and he's helped a lot to organize the event and drive this event forward. So thanks a lot, Mario. Secondly, to Gabriel Lamont, who is going to speak in a second. He's our Western chapter head, but also our online event guru. So thanks, as always, to Gabriel for his efforts. And of course, thank you to our presenters and our panelists who are going to join us. We've got some really interesting people coming up, and that's really fantastic for all of us. So now I'm going to hand over to Gabrielle to introduce the next section of the event. And have a great event, and I hope to meet you in the online networking part of the event later.
Hello, everybody. Very happy to be with you tonight. Also very happy to support the association. As I mentioned, my name is Gabriel Lehmann, and I'm head of the Western chapter for the SFTA. My journey also started about 4 years ago, and now I'm very happy to still support the association, particularly into this COVID-19 situation, supporting to switch into a more, I would say, online model. But I think you are here tonight to learn and to exchange about quantum computing. So what I will do, I will directly hand over to our first keynote speaker. Renato, floor is yours. Please unmute yourself.
Hey, thank you very much. I will just briefly start the screen sharing. And okay, I hope the slides are visible. So oh, somehow there's still something strange. I think it's not the right screen that you're seeing. Anyway, I'll do it later. Okay, so welcome, and I'm very happy to talk here about my actually research topic. I'm a researcher at ETH Zurich, working in the area of quantum computing, quantum information processing in general, and actually also the foundations of quantum theory. And I would like to start explaining a bit what is behind quantum computing, what are the ideas that led to this idea. And in order to do so, I'm sorry, I have to somehow change the sharing for a moment because I think it's actually showing the wrong screen. Just a moment. Okay, now I think it's better. So I'm actually starting to talk very briefly about quantum physics, which is of course behind the idea of quantum computing in general. Quantum physics is, by the way, by now quite old field. I think more than 100 years ago, it was actually Einstein who discovered that the laws of nature on the very small scale are extremely different from what we are used to. And I will point out one of these differences, which is also one of the elements that make this whole thing so interesting today for data processing. So if you really zoom into the small and smaller scale, and at the end the scale of atoms, you have at the end individual particles. And you can think of these particles as particles that have very few properties. And one of the properties is, for example, that they can have a direction. We talk about the spin of a particle. Now this spin, we can today manipulate that. We can, for example, turn the spin of such a particle. And therefore, in principle, also encode information in it. And I will come to that just a little bit later. But what is really different, I just said before that in the quantum world, we have very different properties from what we are used to in our daily life. One of these very special properties is what people call quantum entanglement. Quantum entanglement is the property that kind of two particles can be connected in a way which has the following consequences. If I connect two particles, and today we can actually create such entangled particles. If we now manipulate one of them, let's say the one that you see on the left. So for example, I kind of manipulate it in such a way that the direction of this, what I call spin, is diagonal, then it will immediately happen that the other particle that was previously entangled with the first one will also take on a diagonal direction. And this is actually true. This can be verified experimentally, and because this is a feature which is kind of really surprising. I should really maybe go back once more. You manipulate one thing, and the other thing, which can be arbitrarily far away, takes up the same direction that you somehow choose on one of the particles. This is a feature that Einstein called the spooky action at the distance, and he actually didn't really believe in that. He said this is actually a consequence of the theory, but it's so strange that it cannot really be true. And it took experimentalists almost a century, I think, to really verify that in an experiment, that this has been done. This is one of the headlines, which was actually the New York Times, which is quite recent, actually just less than 6 years ago. And you see here the title, sorry, Einstein quantum study suggests spooky action is real. So it was really verified that particles, even if they are very far away from each other, can have this correlated behavior. So that's one of the things that, of course, makes quantum mechanics extremely fascinating, just as a fundamental discipline, to know that there are these things down there if we zoom in. But these are, of course, also properties that suggest that we can do something with them. So we can ask, what are applications of this? Maybe we can show this picture here. If you think about that, if two particles can somehow have the same properties immediately, if I manipulate one, then the other has kind of the same behavior, that suggests that I can, for example, use it for communication. And indeed, today we have applications like quantum cryptography. I will not go further into that. I will focus on computing, but this comes out of the same fundamental features that quantum mechanics offers. So the question is really, how do we exploit that? And it really took now almost 100 years since the invention, since we saw these interesting behaviors, until we were technologically in the position to exploit them. But this is now possible, and let's say, cartoon way of thinking of it is that we can now put this quantum behavior, into our labs and really manipulate individual particles at our will. So why is this interesting for computing? I guess most of you are familiar with the fact that computers, as we know them today, encode the information binary. So everything is at the end represented as a generally very long sequence of zeros and ones. Even as I speak here, everything is transmitted in this way. And of course, we can, in principle, encode things into physical information carriers. So what that means is that we can say, if you have a zero, we say this could be represented as something that points up, for example, a magnetic field that points up, and one is a magnetic field that points down. This is actually how it's done, for example, on a hard drive. Now, if you do the same thing with elementary particles, so if you encode the information into individual particles that have quantum behavior, we can do more with them than just regarding them as carriers of the values zeros and one. And this is illustrated here. So this is one of what we call a quantum computing circuit. So you should think of each of the three particles that you see here as like the analog of what is in a classical computer, a bit, a 0 or a 1. And of course, a classical computer also has such circuits. And the circuit tells you, for example, take the first bit and add to it the second bit and so on. And arbitrarily complicated applications can essentially be created by manipulating bits. But now the idea of quantum computing is, instead of manipulating bits, we are manipulating so-called qubits. And the qubits are these elementary particles that I was just talking about. And with them, we can do much more than just, as I said, somehow encoding zeros and ones. One of the things we can do is to create entanglement between them. And this particular circuit that you see here would actually build up such an entangled state, as we in physics say, between the second and third particle you see here. So these particles now have the property that if you measure one, if you look at one or put it in a certain direction, then the other one, its partner, will immediately emit the same direction. Now, of course, a quantum computer will need more than just two, but you can essentially think of a quantum computer as a device that has these individual particles, encodes information into them, and then manipulates the individual particles in a clever way so that you can solve a certain problem that you would like to solve. For example, in finance, as we will hear just, I think, in a few minutes. Now, what does this actually now mean? I mean, why is this more powerful? And maybe the best way to see why this is so much more powerful than a classical computer is if you just ask yourself, how many different states can a bit, or now a byte, which are 8 bits, admit? So if you just think of a computer, everything of a conventional computer, and we talk about bytes, and the bytes are 8 bits, and 8 bits, if you think about how many possibilities are there to choose these 8 bits, there are 2 to the 8. So there are 256 possibilities. Now for a quantum computer, this is much bigger, because instead of just choosing zeros and ones, you can entangle each of the particles with any of the others in different ways. And I will now not go into the details of how you do that, but just mention that the number of possible states in which this system can end up, if you just have 8 qubits, is extremely much larger than what you have for classical bits. So you have, in this case, of just 8 qubits, which we could call that the qubit, 10 to the 77 possibilities. And as you increase the number, this actually grows doubly exponentially. So it's an enormously large number of states this can admit. And now you can imagine that if we manage to control this in a clever way, we can get a lot of computing power out of that. And that's indeed what a quantum computer is doing. So we have many of these qubits. And okay, this was the cartoon, how a real quantum computer, you may have seen this picture in the news. This was the 2019 prototype from Google, looks like this. And what you see here is actually mostly the fridge. When you go to into the inside, you will see that there is something like a chip. This is actually not what is in the Google computer, but this is maybe a more illustrative example. So this is a chip that really contains ions. These are little dots as indicated on the right. And each of these ions is one of these particles that can now carry information, as I showed on the previous slide. So it's really physically there. So what I showed in the previous slide is actually realized by having little particles on a chip that can be manipulated by electrical forces, for example, on that chip. There are also other architectures like superconducting qubits. So today we have still not agreed on what platform will really make the race. So there are different, for example, elementary particles you could use for representing information, but instead of particles, you could also use what we sometimes call artificial particles, which are essentially systems that behave like particles that have the same quantum behavior, but are actually just electronic circuits, like this superconducting circuit that we also develop at ETH. So maybe I'm almost at the end, but one message that is very important to me is that, and it was said before, that in Switzerland, I think we are extremely strong in research in quantum technology. We were actually already in the year 2000 starting to explore this area. And there are hundreds of researchers who really made a lot of progress there. And now it's the time to really collect the fruits of that effort in some way. Now it's getting interesting for applications. But in order to do that, we, of course, need people who understand these devices. And therefore, ETH has started a program, a master program in quantum engineering. So this is now a topic you can actually take as your main study in the master. There's also the software side. So you can imagine that as these computers no longer just use zeros and ones, the way to manipulate, you need to really have an understanding of quantum physics to actually program these devices. And so we also need to essentially educate a new generation of software engineers. And just as an example, this is one of my collaborators, one member of my group, who was giving an online course on quantum computing. And you see maybe the little number here on the bottom. So there were thousands of students who were actually interested to learn in this new field and this new skill that will be necessary to actually explore these devices. And once you're really good at that, if you can actually program computers, you can do interesting things, and not only harmless things. Maybe you have seen also in the news, this was actually already, I think also 1 or 2 years ago, that people realized that quantum computers can also be used to do for example, hack crypto system or break crypto systems. And I have here a little slide. This is maybe more for the specialists. This on the left, you see different public key crypto systems on the top that are actually used quite frequently today when we do internet banking. And they are based on certain problems, on mathematical problems that are supposed to be hard to solve. And now quantum computers can solve them if you have an appropriate algorithm. So here we really have already the algorithms ready. So if someone gives me a sufficiently large quantum computer, I could now run these algorithms and break these crypto systems that are used today. The reason why I cannot actually do it is that the quantum the prototypes of computers we have today are far too small to run the corresponding algorithms. But it's clearly a danger, and we have to think about countermeasures to that. Then, maybe to put that a bit in context, the way I see it today, the state of the art, is that we are really at the very beginning. So maybe one can compare the development of quantum computers by the state we had maybe very shortly after the Second World War, where an individual bit in a computer required an actual quite large device to be operated on. And today, when you compare the left picture with the right, these are now a few qubits quantum computers, this time from IBM. It's roughly of the same size. So you see, we have a big problem. We have a big challenge to actually scale things down, because we need, of course, like for classical computer, millions of qubits to run applications like the ones I mentioned before. But luckily, there are also others that we can already do with smaller devices. And I guess we will hear a bit more about that just in a minute. I think that's already all I wanted to say, except, again, stressing this, I think, for me, most important point. There is a network of quantum scientists in Switzerland. It's called a National Center of Competence, which existed since several years. And this has really put ETH in particular, Switzerland and ETH in particular, into a position where we have expertise in all these areas. So we have in the different platforms that are in the race for quantum computers, experts who are at the frontiers of research, but also on the software side and on the theory side. And now I think the big challenge is now to use this momentum and actually profit from it. I think we didn't do that so well in the area of classical, conventional computing, where we also had quite an advantage at the very beginning, but we didn't use that commercially. I think we can do that differently, or I hope we will be able to do that better this time in the area of quantum computing. Okay, that's already all I wanted to say. So thanks a lot for your attention. And then I think I hand back to our moderator.
Okay, so thank you, Renato, for this introductions to quantum computing. I think it's now also time to switch to a more application sides. So I will shortly hand over to Professor Elena Yunderain. Elena Yunderain has some experience in the banking industry. She worked also directly for IBM, a company you know well, and now she is also professor at the EI Business School in Madrid, if I'm right. I will share the profile of Elena directly in the chat so that you can perhaps discover this more in depth. But if you are ready, Elena, I will hand over to you.
Thank you, Gabriel. Let me share my slides. Okay. Can you see my slides? Yes, right? Okay. All right, well, thank you everyone for being here and your interest in quantum computing, and thank you so much for the invitation to speak here about quantum computing and finance. So my experience is in linking research and development into business applicability. So that's what I'm going to be doing today. I'm going to continue with the presentation that Professor Renato just did, and I'm going to explain more in detail how this applies to finance. And I'm going to do it from a practical point of view to kind of translate all the physics into the business application. So when we think about quantum computing, right, we think about why should I use quantum? What is the benefit of using quantum computing, right? If I work for a financial institution, like in my case, I've done a lot of consulting for financial institutions. I've also worked at a bank. And when I worked at IBM, I created the business unit for finance, for quantum, and I worked closely with companies. And the first question that companies asked is what is the benefit that I can get from quantum computers? So it's great that they work on quantum physics. We all love that. It's very cool. But you know, what's the benefit? So if we can categorize the benefit areas of quantum into 3, so we know that quantum computers are good to solve mathematically challenging problems, and this can be categorized into 3 types of problems that I'll explain a bit more in detail. One is about optimization, right? So making something as perfect as possible, looking for the optimal solution, right? The scenario simulation, so creating all the what if you want to think about different options, different possibilities, and then the classic artificial intelligence and machine learning, right? So I'll go into each of them. So when we think about optimization, when we approach it with the classical way, we can think of it if we have the different possibilities, different options. So here in the left, we see this 3 graphs, right? The red route, the blue route, and the black route. If we were going to choose which is the best one for, you know, a specific goal, we would look at them in kind of like an iterative way, right? So we would compare the red with the blue, which one is better, the blue with the black, and so on, right? So this is not a bad approach. It really works well. When this approach fails is if we are short in time. So if we have one of the biggest limitations we have, especially in finance, is that sometimes we are very short in time to provide a solution, right? So if we don't have enough time, we can run through all the different options that we have to choose the best one. Now, however, if we look in the figure in the right, over here, if we were going to look at from a quantum computing point of view, if we mapped our problem to a quantum algorithm, we could say that in a very simplified way that we're analyzing all the options, all the possibilities that we have in a simultaneous way, right? So that means that what we're actually doing is reducing the number of steps that we take to solve this problem. So we would be loading the data to the quantum algorithms, the quantum circuits that Renato explained earlier, and then we would apply superposition and entanglement, the properties that he mentioned, and then we would look at intrinsically from a hardware level. We're calculating all the options, we're mapping all the options, and choosing which is the best one. So that means that we're reducing the number of steps, and we would get faster to the solution we're looking for. Now, the underlying algorithm in quantum computing that runs this optimization problem, it's called the quantum approximate optimization algorithm. And the properties that it has is that it brings a heuristic improved runtime and an increased quality. So it's faster, we could say it's faster, and we could say that it brings a better quality to the solution, right? And something good that it has is that it works very well, or actually maybe that's very optimistic. It works well with the current quantum computers, what we call the near-term quantum computers. So these are the systems that we have today that have, as we all know, that they have noise, so they're not perfect in that sense. So this is a very promising algorithm. Now, the next area in which we can computing, this is the scenario simulation that I mentioned earlier. So one of the problems we have with scenario simulation, if we want to think about all the different scenarios that we have, all the different what ifs, we often don't have enough time to run all these possibilities, right? So we are short of them. We have to make some estimates, right? So this, if we're thinking about the probability distribution that we're creating, maybe it's not the most optimal one. But with a quantum computer, in a sense, when we do this probability distribution, because of the properties of quantum, the fact that we're mapping everything to what I like to call a multi-dimension space, or a 3D if you want, if it makes it easier to understand, you're mapping the data more efficiently, and you're creating this probability distribution that's more efficient. And what it's doing is that it's improving the sampling, and therefore when you perform the distribution, you need to run less scenarios to get to the most accurate solution. So in this case, what you're getting is speed up in the solution. This algorithm, that's the underlying algorithm that runs the scenario simulation. This is the type of Monte Carlo simulations that we're very familiar with. It's called the quantum amplitude estimator, and actually it delivers a quadratic speed up, so from the number of samples that you have, and it also improves the quality of the solution, so it's more accurate. Now, however, there's always a however, right? This algorithm, it really requires a more mature quantum system. By this, I mean a quantum system that has less error rate. And I'll talk a bit more about this error factor and how it plays and how do we need to think about it when we're developing an algorithm or when we're mapping a problem, right? So this, the Monte Carlo is, I'll talk more about, what is one of the most tested algorithms. The problems that companies have here that usually when they talk about why they want to test quantum for the Monte Carlo simulations is because they have one is the time, as I mentioned, that they don't have enough time to run all the scenarios. They take days, right? And they need to do the scenarios maybe in minutes, maybe in less than an hour. And also the time and the money spent in high performance computing, because most of the companies, most of the banks, they rent high performance computing, and if they're running complex calculation, the longer it takes, the more money they have to pay, right? So that's another reason why they want to test this algorithms in quantum computing to reduce the time run. And now the last category, the third category, it's artificial intelligence and machine learning. So when we think about AI and machine learning, one of the problems that we're running into, and we see this a lot, is all this false positives, right? That we get. The fact that when we're creating the model, when we're training the model, and we're to actually build the model, to do the classification, sometimes we are unable to properly separate the different classes, right? So if we see here the figure on the left, right, it would be no way to have to find a division here between the red and the blue balls, right? However, with quantum, we would map this data points into a higher dimension, right? So like this sphere, qubit kind of mode, and this we could simplify and say that by mapping it into the sphere, into this 3-dimension, we would be able to come up with hyperplanes that would separate the blue from the red, and we would avoid the false positives. As you may be aware, the false positives are costing a lot of money for financial institutions. So if you think about fraud, for example, in payments, in all the cards, there's a 70% false positive rate for fraud classification. So that's a big one, and that would be really beneficial if we can get algorithms that are run by quantum computers, so quantum machine learning algorithms that are more accurate. And this is exactly what we can get. So with the underlying algorithm, the quantum support vector machine, what we get is more, we get an increased accuracy because we can find patterns that usually we would not be able to find with a regular classical computer. We could find these relations between data, especially when we create the model of the algorithm. Now, however, this is one of the algorithms that's a bit of an unknown, like a wild card. We know they run with near-term quantum systems, but the tests that have been done so far, the benefits are not so clear. So there's a lot of tests to actually find if we can scale the problems and the benefits really scale as with the current computers. So these are the 3 big areas that we can benefit from quantum. So optimization, the Monte Carlo, and the artificial intelligence. And in all of them, as you can see, we have in common that we increase the accuracy. So we find better solutions, and in most of them, we can even do this in a faster time period. Now, how did this map to finance, right? So this are just some examples financial problems and how they fit into each of the buckets of the algorithms and the areas in which quantum can bring benefits. So one is, for example, the ATM machines, for getting the money. How do you manage the cash? So how do you adjust the amount of money that you need for each of those ATMs? How do you allocate it? And this brings a lot of overhead costs, right? If you don't have enough money in an ATM or you put too much, etc. This is one of the biggest optimization problems for banks. Another is trade settlements. So if you think about trading, the problems that you have obviously is when you have the market and all the stocks are trading, and even with, for example, you think about foreign exchange, there's a time frame, right, when the market closes. So if you can do better, a more optimized trajectory, you can actually do the best trade and end it up on time. So before the market before you get caught up in the window of the market. Another is the portfolio, right? So if you think about portfolio, it's an optimization problem. It's a type of a combinatorial problem. So how do we handle this? Obviously, with the quantum computing algorithms, you can actually enhance the investment decision by analyzing better the combination of assets and rebalance your portfolio, right? Then if we go to the next category for simulation, the type of problems that fit here is one is obviously risk. We think about how to mitigate risk, how to simulate better models, how to run these endless scenarios, so endless what-if scenarios, so you can actually understand better the risk. And this applies directly for derivative pricing. So how you can improve the asset pricing. And actually, there was a test that was done at IBM, and I don't know if we can talk about it later in the panel, but you can see it. There was a visual demonstration on how you price the derivative European call option, and how you got a much better accuracy with the quantum computer versus the classical computer, and how actually you needed fewer samples to get to that optimal solution. Right, and then for fraud detection, you can enhance the tests that are being done with, this falls into the machine learning category. So how do I find those patterns to flag false activities? And then finally, obviously for client or asset scoring, if I want to do a credit scoring, if I want to find the profile of a client, if I want to do a better profile, I can do it with more accuracy, finding all these patterns. Especially today with the amount of data that we have to profile clients. If you think about like even behavioral data, that's really hard to match, right? And also the credit, the asset scoring, right? If we think about when we're building the portfolio, how do we get it? How do we analyze better the asset to ensure, for example, that we don't have non-performing loans? So this is the match between the algorithms, so the categories, and the different use cases. And I was mentioning earlier, so the developments when we think about an algorithm for quantum computing, given the stage of the technology that we still have a few amount of qubits, and the qubit quality, or if you want to talk about the quantum volume, which is an industry measure that talks about how well the qubits work, what is the error rate, etc. So what companies are doing, they're working in two big areas. One is develop the use cases. So the use cases I just mentioned, for, like I said, trading, credit scoring, etc. But what they're also doing is improving the foundation. So they're working and improving those algorithms so they work better with the current near-term computers. So they're doing some tests in how to improve the data loading. So when I load all my data into my quantum algorithm, into the circuit, and I can put it better in superposition and entanglement. Then they also work in this circuit in simplifying the circuit, reducing the amount of calculations and the amount of steps, the amount of instructions, if you will, that I have in my circuit, so that it will work better with the current quantum computer, and also the final part of the reading when I want to get the solution, because the current computers, so Renato was mentioning, we have different technologies, superconducting qubits, we have trapped ions, and we don't really know yet which one is going to be the one that will reduce the error rate, and we will be able to help us scale the technology. So this is an illustrative list of the financial institutions that are testing quantum. I mean, it's growing all the time. This is public information. I'm sure there's a lot of private that we don't know. So ABN AMRO, for example, they're working in the security piece, in creating secure communications to ensure their data is transferred more securely. So in between the branches and with clients. So they're doing that for to enable, let's say, for mobile banking. Barclays is working on the trading example that I told you earlier. So they have been testing how to do and how to improve the optimization problem for trading, specifically for foreign exchange. BBVA has been doing some tests to test optimization, to test portfolio, how to build a better asset basket. CaixaBank did some tests for non-performing loans, to identify non-performing loans and mitigate portfolio risk. Now, CaixaBank, Commonwealth Bank of Australia, they've done also portfolio, but they focus more on the rebalancing. Goldman Sachs has been focused in Monte Carlo simulations for derivative pricing. JPMC has done the same, a lot of derivative pricing. And also they worked in fraud. Lloyds Bank is working as well in derivative pricing in their case for European and Asian calls. And Mizuho is working on the risk, and improving the credit risk for portfolio management as well. NatWest also is working on optimization of portfolio, in their case for high liquidity assets. And then Santander is working on derivative pricing. So as you can see, most of the companies, the big themes are Monte Carlo simulations and optimization, right? Now we think about when are things going to happen. So that's one of those hard questions to answer. But if we think about the progression, right? So the 2015s, like the last 5 years ago, right? The tests that were being done were more proof of technology, to test that the technology was viable, that things were working, very small tests. We had very few microqubits, and it was more to test that, hey, this technology really works, right? But as the market adoption starts to increase, where we are right now, it's more about companies are testing. So those that are more like early adopters are testing the proof of concepts, and they're learning how to use quantum. They're learning the skills, and they're getting ready in the organization, setting up departments and areas that are working on quantum computing, right? The next thing that will happen in this decade, we will see the early majority and the late majority as the technology improves, and we get to the thousands of qubits that is expected to happen like in 5 years, more or less. Then we will get tests that are really, we'll start seeing that we're testing use cases to see the business benefit and what's a competitive advantage. So we will transition from toy examples to really the examples, larger examples, based on those toy examples that show the benefit and that would actually be running with current operations. And then finally, obviously, in the 2030s, when we reach that million threshold, we will start seeing replacements of current HPC legacy systems with quantum computers. Now, if you want to learn more about quantum, I recommend, if you want to get an overview, that you read this paper that we did a while ago while I was working at IBM. This is a paper that has an overview of applicability, state of the art, and all the potential quantum uses for finance. It also reviews everything, so everything that I've presented and part of what Renato presented. So what is quantum computing, the challenging finance and problems in finance that match into quantum, demonstrations as well, and then also what are the technical challenges. And then there was a question about what are the skills. Someone mentioned what are the skills to work in quantum. So basically, I mean, obviously the best would be to have the square here, quantum information, but obviously that's very rare. They're skilled, very, very few, if not quantum physics, and also if not linear algebra. That's what we've seen with clients. When I work with companies, that I continue working as of today, the profiles of people are either very strong in math, they know quantum physics, or they know quantum information. And that's it from my side. Thank you very much.
Thank you, Elena, for your contribution. So now that we know not everything, but a lot, it's time to switch for the panel discussions. And for that, I will hand over directly to Daniel, our president, who will have a short word about our panelists. It's to you. Floor is yours.
Thank you, Gabriel. And thank you, Alina. Thank you, Renato, for the presentations. We're now going to have a short panel discussion. We're running over in time, in terms of time, but I think we can have a good panel discussion now with some questions that we've prepared and some that have been provided in the Q&A section in the chat, I can see. In that respect, I would like to welcome the panelists onto the on-screen. So if you guys could click your camera on and your mic on. So we'll add Jay Oberoi and Krista Zufald to the panel. And Mario, of course, yes. Thank you. And just wait for Alina and Renato to join as well. In the meantime, maybe Jay and Krista and Mario, you could briefly introduce yourselves before we start the panel. Would you like to go first, Jay?
Yeah, sure. So my name is Jay Oberoi. We've been in wealth management, private banking for 20 years with a company called Synergy Asset Management. And then Swiss banking secrecy sort of vanished from under our feet. And we look at the transformation of wealth management. I think there's been a massive transformation in wealth management because of many factors. And one of them is because of technology. So we started focusing on technology and wealth tech and fintechs 5 years ago in Geneva. We started the Geneva Wealth Tech Foundation and Forum. So that was to put together the biggest actors in wealth management with the big players in technology to see what is the future and how can we benefit from technology in three main areas. The first is how do we get clients from all around the world? Technology should be able to help us approach clients faster and easier. Second was how to have better performance in our accounts in our portfolios for our clients, and I'm sure technology could help in that. And the third was to become more efficient so that our costs go down. And certainly in that process, while we were doing this for the last 5 years within Synergy Asset Management, we started looking at quantum very seriously 5 years ago. We invested in a few companies in quantum computing and worked on neural networks for trading, for example. And then we moved on to something which we think is very important for Switzerland, which is basically privacy and security of data. We believe that wealth in the future will become digital, whether it's crypto or it's blockchain or something else. The fact is that it is going to be digitalized. At that point, it requires high levels of security because current encryption methods will be broken by quantum computers. So that's what we've been doing. In a nutshell, that's my introduction. So we're very fascinated by the industry.
Thank you. Sounds great. Looking forward to hearing more about that shortly. Krista, would you like to briefly introduce yourself?
Sure. So hi, my name is Krista Zofel. I've been part of the quantum optimization finance team for IBM Research for the past 3 years. And we're basically looking at the two sides of one coin. So first of all, I'm sorry, I'm hearing my echo really bad. Okay. Let's try it like this. Maybe it works better. Okay.
That's better.
Exactly. So basically, working on both sides on quantum research in this field. So we're developing algorithms that can be potentially useful, And then we also work together with the clients to get then the subject matter expertise inside and bring this research algorithm even closer to the application that is in particular important in financial industry.
Thank you. Thanks a lot. Mario, would you like to briefly introduce yourself? I'm trying to unmute you there. There we go.
Yeah, hello everybody. Can you hear me?
Yes.
Okay. Yes, my name is Mario Luoni. I have a background in mathematics and quantum physics actually. And like the last 15 years, I've been working as a quantitative developer and analyst with a big reinsurance company, mostly pricing bespoke derivatives. And I have a personal interest, so it's not a professional interest in quantum computing. And as a volunteer for the Swiss FinTech Association, I thought that might be a topic which could find a lot of interest. It's kind of being hyped to some extent, the quantum computing, and so we are very happy so many people are actually attending this event. And I'm here on the panel. I will ask some questions. I'm not expert in quantum computing, but I'm happy to learn more about it. Thank you.
Thank you. Thanks a lot. Yes, so let's maybe dive into some of the questions, and some of them were, I think, covered by the presentations, which is fine. But let's pick some of these questions to discuss here. One of the first ones we mentioned here was regarding fintech actually, and the applications of quantum computing and the biggest potential to revolutionize fintech, which we thought maybe Jay could answer that or address this question. You're on mute, so I can unmute you. Yes. There we go.
Is it on? Okay. So yeah, I can take you through that. I can take you through some of the applications that are very, very useful. Before I do that, I think I want to tickle everyone's mind a little bit on what quantum computers could do to banking and finance over the next 20, 30, 50, 100 years, because that's very, very interesting. So I just want to give a little story. I think a lot of you may have seen Schrodinger's Cat. Every geek who's in quantum computing has a t-shirt with a cat of Schrodinger. And so I don't know if you know the story of what it is and what it means, but basically in a very quick summary, it's a box. You have a box with a cat inside, and in that box there's a cat plus a little bottle of poison. And you cannot look inside the box. So you see this cat and you're not sure whether she's opened the bottle and taken the poison. So is the cat alive or dead? And that's the eternal question. So the cat, in your perspective as a person observer, the cat is dead or alive or both at the same time. So you don't know its physical state, which is what Renato was talking about. And what is very interesting is in finance, we've known this for the last centuries, since banking ever existed, is that money itself has many, it exists in different faces and states at the same time. Let me give you an example. When you have $1,000 and you put it into the bank account, for you, the money is in the bank account. Now the bank takes the money and lends it out to someone else. So just take any driver or something who takes the money and buys a car with it. In his mind, the money is with him and he's bought a car with it. In your mind, the money is in the bank. So the same, this money, the $1,000 has different states or being used in different ways. Now the implication of that is huge. In the future, we'll be able to do investments in one place, but have the same money being invested in other places. There's a lot of very, very exciting things that could happen. We're talking very, very long term, but superimposition is something which could become a physical thing in the future. So there's those interesting things. Right now, the applications are pretty simple. As I was talking to you at the introduction, neural networks is certainly one of the fields that is leading. simply because of the fact that it emulates a human brain, right? So the predictive powers for fraud detection, for risk assessment are tremendous. And we did that for trading. We started trading 2.5 years ago using neural networks, and our performances are 2% per month consistent basis. But the truth is that none of these actually are forecasting methods. These allow you to provide you with trustworthy and precise information. That's it. The fact is, when we get our buy signals, the system tells us you can buy now, but it doesn't tell us when to sell. So we have half an hour to a span of 2 hours to decide then when the sale period is and when we take our profit. So I don't think these neural networks, they're all okay for allowing to take and consume data, but they're certainly not there to create a black box, unfortunately, that gives you money every hour. So those are not there. But where these fields are going to be, where they are currently being used, I think is quite exciting, is anything which has a price to it, and the market is not efficient. If you look at option pricing models, today we're using Black-Scholes model. Now, Black-Scholes model talks about the fact that markets are assumed to be efficient. Like most models in economic theory are about the fact that everything is efficient. The truth is, pricing on options is not perfect, simply because prices move very fast, so you don't even have time to calculate. The information dissemination is huge, it's very fast these days. And also the wealth is unequally distributed between traders. If you take that into account, it becomes very difficult to price the thing perfectly, unless you're using algorithms that are using post-quantum encryption. For example, Shor's algorithm really helps for factorization. Grover's algorithm for quantum search is something that has been used by traders too. So therefore, you are able to make money on inefficiencies of markets. So yeah, there is. Then there's the whole field of, I'm not going to go too much into all of this, but QRNG, which is quantum random number generations, right? So a lot of that has been talked about because it's important in the field of finance and encryption. So we need numbers that are completely random, and quantum certainly provides that to us. In fact, Samsung came up with a chip called a quantum chip. On their phones, it's a chipset on a CMOS image sensor that detects light, right? Photons that are emitted from LED, and so that generates random numbers. So there are a lot of applications for it. The issue that we're going to face in the future, I feel, is certainly the problem with RSA and the encryption part, and that's what we're focused on. The fact that whether you take Bitcoin today, or so you take blockchain, or you take the standard RSA encryption methods, they all can be broken at some point with our quantum computers.
Thank you. Thanks, Jay. That's really interesting. Great to hear that. I've got another question here, which I would like to ask Krista, and it links to what you were just talking about a bit, Jay, but more specifically to what you're doing, Krista. So you're working at IBM, and we were just interested to know what financial institutions are you already working with, and how can banks access quantum computers?
Sure. Actually, Elena already mentioned like quite a few of them, and she also knows them. But just to mention a few names again, like we're working with banks like JPMC, Goldman Sachs, PayPal. They already have like their internal research institutions, and then they're bringing together some of the research from IBM and some of the research.
It's sorry to interrupt. It's echoing quite badly again. Maybe you can try without your.
I think Jay is not muted, and maybe mute. Then it may be.
Maybe does it work now?
That's better.
Yeah, thanks for that.
Yep.
Thanks a lot. Yeah, exactly. So basically, then this whole program then brings together the researchers from both institutions, from the IBM, from the quantum expertise, and then the subject matter expertise from the banks. And for the access actually of the IBM quantum systems, there's you can say there's two possibilities. So actually, there's a set of publicly available quantum computers. So each and every one of you can literally just go onto the website and create their own accounts and run their own quantum algorithm just as we speak. And then IBM has a full partnership program, which is called the IBM Quantum Network. And then within this partnership network, there's an additional set of quantum computers, which is being made available throughout this partnership then to the financial institutions, where they can then also partially have some dedicated access to run the simulations that are important to them to get a better understanding of all the algorithms that we already talked about.
Thank you. Thanks, Krista. So did I understand correctly? We could log on somewhere. We could log on ourselves and use quantum computer,
Yeah,
quantum
exactly.
computing power like that. Okay. Wow.
Exactly. There is something that is called the IBM Quantum Experience. If you Google for it, you'll find it. And this not only includes like a platform to publicly access the quantum computers, but it also offers a variety of tutorials, of actually a full textbook, which explains some details that are also important for the financial applications, such as quantum machine learning, optimization. So to get started and just to try it out, you can get a lot of material on this platform.
Okay, very cool. That's cool. So no doubt a lot of people will probably do that after this event. Thanks a lot for that insight. One of the topics that kept coming up several times with the questions that were given in advance was security, and especially around cryptocurrencies. So I was wondering if Alina or Renato or both of you could answer a question regarding the security threats to financial institutions. You mentioned quantum cryptography, Renato, and the topic was around general cryptocurrencies that I think some people are, I guess, worried about. So maybe if one of you could answer that or start an answer on that and let us know what you think.
Yeah, I can start maybe with an answer, and maybe Elena can then play a bit more. So for cryptocurrencies, I think there is a relatively, let's say, feasible way out today, because quantum algorithms, I think this was also, I saw some questions in the chat, what one has to be aware of is that a quantum computer doesn't just generically solve any problem faster. We need to really cleverly use the hardware, and we need to develop new algorithms, and that's one task we still have ahead of us. So actually, people usually talk about hardware development. We also need probably equally many people developing new software, and only then can we use to really exploit the power. So for most problems, we don't really know how to solve them faster yet with a quantum computer. And of course, people like, for example, Krista are of course very strongly working in that direction, developing these algorithms on new types of algorithms. Now it happens, and this is maybe an irony of the whole development, that those algorithms or those problems that were used for securing public key cryptography, namely RSA and Diffie-Hellman, were among the first things that could be solved by quantum algorithms, namely Shor's algorithm. But for many other cryptographic problems, like those, they're so-called hash functions or one-way functions, we don't yet have a generic algorithm that solves them. So it's not true that just any cryptographic system will immediately be hacked. What is really in danger are these so-called public key crypto systems, and systems that are based on one-way hashing, as it's called. I think there we still have good alternatives at the moment. So we have hash functions that, for the moment, we don't know how to break with a quantum computer. But this is all potentially a question of time, because as our knowledge in how to use quantum computer progresses, we get better and better at actually also breaking crypto systems. And so there is really a race between those people developing so-called post-quantum cryptography, so that's cryptography that is secure against future quantum algorithms, and those people who are just pushing the software in quantum computing. And you can never be sure in this area. So if someone proposes a new, let's say, crypto system that is based on some different computational problem, there may on the next day be someone who has a quantum algorithm solving it. So there, it's really kind of a race, I would say. However, the other side of this irony is that quantum technology also offers a completely secure way of doing cryptography, namely quantum cryptography. And so this is a type of encryption which is not based on a mathematically difficult problem. So even if you have an arbitrarily good computer, you cannot break such a scheme. The problem with this is that this is a so-called symmetric cryptographic system, and it needs special purpose hardware. So if I want to, let's say, exchange now a message with Krista, I would need a direct optical fiber going from my home here to Krista's home. So we would need completely new infrastructure. And this is, of course, at the moment only accessible to really critical applications, maybe military applications, or for financial institutions who have a storage center somewhere, data center somewhere, and want to connect that securely. So maybe to summarize, I think quantum technology offers at the same time, appears a danger for cryptography, but today it's mostly public key cryptography, so it's the thing we use for e-banking and so on. And at the same time offers a solution to this, which is, however, enormously expensive because it requires a new infrastructure. So, but I'm sure Elena can maybe shed some more light on it from more on the financial side of all that.
Yeah, I can add a bit more. I mean, you did. I'm glad you answered all the crypto for the currency piece, because that I'm less familiar with. But so the financial institutions are starting to get ready for the whole cryptography and the challenge, the threat for quantum. It's a bit similar to like the Y2K, right? Those of you that remember how companies started to get ready for that. So what they're doing is they're putting up a plan for quantum security, and they're analyzing all the data that they have and classifying it to see which data is at risk. You know, when if and when we get the current data can be hacked, to put it simple. And they're also working in getting more agile in terms of the crypto agility to be able to change their schemes for cryptography. And those are the two lines of actions that they're doing to get ready for quantum cryptography.
Yeah, briefly add something, because one aspect which is really important is kind of the timeline of this whole development. So some people are saying usually, okay, quantum computers are still maybe 10 or 20 years away, or at least these types of quantum computers that could run Shor's algorithm, which would break public key crypto systems. But we have to take into account that if you encrypt something today, then it can still be decrypted by a quantum computer maybe in 20 years. So, and the additional thing is that if you want to change our public key crypto infrastructure, so if you want to have new systems that are used for e-banking, this takes a very long time. So if you start to change the system now, we will probably only be ready in 10 years. So if we now take a kind of, from the cryptographic side, pessimistic scenario that quantum computers will become available in 10 years or so, then we really are now very much urged to start changing our current cryptographic means. And so it's not something we can leave for the future. That's what I think is extremely important to realize. We have to start thinking about new cryptographic methods right now, if it's not already a bit late.
Yeah, it is the number one priority when the quantum adoption roadmaps for all institutions, but more so for financial institutions that are transferring, very important data.
Thank you. Thanks a lot. Mario, did you want to ask one of your questions that you prepared? I just need to unmute you. There we go. No. There.
I still go. Can you hear
me? We can hear you now.
Okay.
Yes.
Okay. Well, I was wondering, I mean, as I said in my introduction, there is a certain degree of hype in the quantum computing topic, and I was wondering, there are problems that can be solved more efficiently with a quantum computer and others that can't. I mean, now I can't give you an example. I've just read it and I don't remember the details, but I think there are problems that are more easily solved with the quantum computers, but not all problems. Some problems, even with the quantum computer, cannot be solved more efficiently than with a classical computer. And I was wondering if there was some kind of let's say theoretical result, a simple criterion, which would allow me to decide whether or not the problem is more efficiently solvable by a quantum computer as opposed to a classical computer. I don't know who could answer that question.
Maybe we can give a chance to answer that if either of you could.
Sure. I can say a couple of words to that. Unfortunately, I'd say a simple criterion is nothing too easy in this area. Since maybe let's start somewhere else. So as you also said, like there are some problems where you wouldn't want to use a quantum computer. For example, in addition, you'll still use a classical computer for this. But the quantum computer, or what we expect is rather that classical and quantum computers will work in a kind of like a symbiosis. So they will work together rather than the quantum computer completely replacing the classical computer. Because as mentioned, there are some problems where the classical computer does perfectly well, and in addition, a quantum computer can require many more operations compared to a classical system. But there are those problems which you can categorize according to the quantum algorithms that we know these days that have an advantage, and then basically determine from these types of quantum algorithm classes where to go. But there's not this one simple criterion.
I mean, some of the people attending this event was asking if it was correct to say that not all, now I'm getting very technical, not all NP-complete problems can be solved with a quantum computer, or better solved.
Yeah. I mean, yeah. Okay, that this is a very legitimate question, and actually, I guess a big part of the current research is whether we can find good heuristics with the quantum computer, or better heuristics with the quantum computer compared to the heuristics that we currently use with classical computers to find approximate solutions to those NP hard problems. So I guess you also need to work on this level. So we're not only investigating like what can we solve absolutely better, but is there also a heuristic approach due to the properties of quantum mechanics, which we can use to find better but approximate solutions.
Okay. I have another question. I don't know who I should ask. Namely, we know from other technological developments that military funded research sometimes is. Do I have an echo myself now?
A bit.
No.
It's okay. I think it's okay now.
Okay. Yeah, we know that sometimes, or maybe frequently, who knows, military funded research is much more ahead compared to civil research and development. And obviously, it's very difficult to have an idea how much further they are, because everything is secret and hidden. But I don't know if any of you does have some inkling as to the developments in like, I don't know, the Department of Defense in the United States or China or wherever, maybe China even less, what they are doing, if they are ahead of, and how much they are ahead of civil R&D. It's difficult and hypothetical question, I know, but maybe anybody does have some.
Maybe I can say something, because actually We also get even research money from the US Air Force, which sounds maybe a bit strange, but they usually research funding in the US is channeled via actually defense organizations. And therefore, I know a bit what they are doing and interested in. And I think the main worry here is that the Chinese are currently just extremely fast and investing a lot of money into that, in particular also in quantum cryptography. This is a bit different from quantum computing. But if you look at the field of quantum cryptography, there I would say the Chinese are, at least on the experimental side, clearly leading. And this is in principle, of course, a worry, and the US is following that. But as far as I can see, this is mostly public research. And I think I'm pretty confident in saying that, because if you work in the area, you know, let's say the young people who are educated worldwide in this field. And if there is some, let's say, drain of these people, that they suddenly disappear from the surface, then you could get worried. But this is not really happening. They're mostly going to companies, and we still know what they are doing. So if the military organizations were ahead, they would also need to educate young people in this area. And I don't think this is actually feasible in practice. The usual way is that they go via the public universities, or at least research institutions.
So it's still a small world.
My conclusion, and of course I cannot be sure, but from what all I know is that in quantum computing and quantum cryptography, we know essentially in the public domain what's going on, more or less. I mean, of course, not the details, but I think they are not ways ahead.
Okay, good to know.
They're also doing a lot of tests. Sorry, now I have the echo. So yeah, they're doing a lot of tests for GPS and the sensor and the quantum sensing side. That is, they're doing big investments from the military in the US, especially.
Okay. Thank you. Thanks a lot. Unfortunately, we're going to have to come to the end of our panel because we're quite far over our time so far, and I want to give people a chance to join the networking part of the event, and also they can ask some questions, I think, to the speakers and generally discuss in that aspect of the event. So thank you all very much for your contributions, and there are actually some tables with the names of the speakers. The speakers are not forced to go to that table, but that would be great if you guys could go there, and some people might have some more questions for you there, and to sort of e-meet you. That would be great. And thank you all for attending, and yeah, please enjoy the next part of the event. So also just to note, we did have 2 floors of the event at the beginning, but it's just 1 floor, which is relatively full now. So there's no need to go up onto the so-called second floor of the platform. So with that, I wish you a good networking session. Thank you very much.
Thank you.